I am Dr. Neeraj Kaur Mishra and welcome to this session on the core component of IBM Qiskit. In this video lecture, I will explore how Qiskit is a structured layer. We know in Qiskit there are many layers like Terra, AR, Ignis and Aqua, and how this layers is actually useful for different scenario of building a quantum circuits and the simulations, and we analyze the errors, and then how the real quantum world application is possible by using IBM Qiskit. So we will also understand how the reversible circuits are optimized with the help of templates based on the RC Weaver, and how this code will be mapped to the Qiskit, and then we have to go for the real quantum worlds. Okay, so if you are interested in this quantum computing domain, or you want to learn the Qiskit or the quantum circuit design, so this video lecture will give you the real or practical understanding about the simulators or the core component of IBM Qiskit. So uh, so we know why the quantum computing is now it is more popular, because this quantum computer can solve a problem which much faster than classical computers. So let's explore how IBM Qiskit is possible to design quantum circuits, and then we'll go to the real world applications. So now we know every year we are celebrating a quantum day. So today we are celebrating a quantum world day on 14th April. So this day is very highlight. It is showing the power of quantum science, and this is a foundation of the next generation technology like quantum technology. So now we know there are many benchmark tools of quantum circuits. We have shown in the slides like IBM have a tool that is Qiskit, and Microsoft is Quantum Development Kit, and also the Rigetti and many other company. The tools is highlighted in this slide. So our agenda is in this session to discuss about the IBM Qiskit, because the IBM Qiskit is a real quantum hardware. So the engineers who is developed this quantum IBM Qiskit, so they are using a quantum computing framework like SDK that uh, which is helpful to connect your algorithms and do the simulations or do the many real quantum computing hardware related task. So in the IBM Qiskit, what is the benchmark metrics? So in this slide, I am discussing about the benchmark metrics. So the first parameter is the gate fidelity. So gate fidelity is like accuracy, how the quantum circuit perform, uh, how the quantum circuit performed with the real or ideal operations. So mostly in the simulations, if the higher fidelity, it shows that less error in a quantum circuits, and if a low fidelity, so that means it is unreliable computations or more errors in the computations during the computation in the quantum gates. So of course if the fidelity value is 1, that means all the perfect gates are whatever the gates in the quantum circuits are performing a perfect simulations. Okay, another parameter is the quantum volume. So quantum volume given the overall capability of the performance. So what is overall capability? So capability is nothing is like a gate fidelity or the connectivity or the error rates, or what are the how many qubits are in the quantum circuits. And the third parameter is the quantum depth or the width. So first we are going to discuss what is depth of a quantum circuit. So depth is the number of sequential gates which involve in the quantum circuit, and width is like a number of qubits we use in our quantum circuit. It is like a resource of whole circuit. Okay, so next parameter is the error rate. So error rate is actually a probability that a quantum operation fail. That means if the gate is not working, that means it is an error in the gate rate. So what is a readout error? So that is also a performance parameter of the quantum circuits analysis. So another parameter is T1 and T2 times. It is like a coherence times. Okay, so if suppose that if we measure the T1, it is showing a relaxation time. So relaxation times, it is like energy loss in a whole system. And the T2 time is a dephasing time. So what is dephasing time? It is showing is the loss of phase actually in loss of phase information. Okay, so another parameter is the execution time. So execution time is the time to run a quantum circuits in the backend simulations platform. So that means what is a gate operation time? We have to look in this execution time, and we have also the measured time of whole computation system. Okay, so if you design some kind of quantum circuit, we need to look all these benchmark parameters which will be useful for novel research if all these parameters to be more optimized or more good. Okay, in my next slide is I am showing the benchmark metrics. So accuracy is actually denotes the fidelity or error rate. And scalability, mostly people are saying what is the scalability. So what is scalability? Scalability means the circuit depth or the width or the quantum volume, which we have already discussed all these parameters in the previous slide. And the another parameter is the stability. So stability denotes the T1 and T2 times in the benchmark performance parameter. And also the last parameter is a performance, which is denote execution time. Now I am showing you some kind of demo circuit which is showing the fidelity, which we have seen in the previous slide. Like fidelity is one, that means the gate, the perfect gate of implementation or the perfect operations. It is like ideal conditions. Okay, so here I am just showing you some Qiskit code, which is like you can see this 4 lines, which is like a library files we have used here, and this is showing we have a circuit in which 3 lines are input and 2 lines are the output. Means we have to measure these 2 line only. Okay, in the first line we have put a NOT gate. Is like we have putting a NOT gate, and in the second line is also we have putting a NOT gate according to this. Okay, now we have 3 line. So suppose that this is the Q naught. Okay, and Q1, and this is Q2, and here the third line. Suppose that the third line denotes the CCX gate. It is like a 2 control point and the 1 target qubit. Okay, and the last line is denotes is like 1 control line on the first qubit and in the second qubit. So it is like a complete circuit. If we uh, implement in a quantum circuit, is like complete circuit. So this 2 line is actually used to measure output. We have measuring output here, and we have measuring output here, because it is showing 1 and 2. Okay, so here this line is actually used to identify the fidelity. Okay, so let's we go and implement this real quantum circuit in a IBM Qiskit. So this is my Jupyter notebook, and here I implemented this circuit. It is like a half adder, and I use the same code what I discussed in my slide, and I run this code on the backend simulators. Okay, that is ideal simulators. Of course, it is not a real hardware. It is like a only backend simulations. And here I use the fidelity to measure the fidelity of quantum circuits what I design in my circuit. So I just now go to run this whole code, and I we have seen in this, after execution, you just see the gate fidelity is 1. Of course, it is an ideal fidelity. Okay, perfect gate implementations. And we have seen here the output is 110. That means the last two output is okay. So here the last first qubit is 0, last second qubit is 1, and the last qubit is 1. Okay, so that is all about this circuit, means how to measure a fidelity. That is the main intention to design this circuit. So another thing is that is the what are the core components in IBM Qiskit? We know there are many things like Qiskit, Terra, Aqua, Ignis. Okay, so what is the physical significance? So this is the actually to Qiskit, how it is connected to the hardware. So all these layer is actually required to connect your uh, quantum assembly code to the real quantum hardware. In this way, there are many layers like Terra, Ignis, Aqua, and AR. Every core component have a significance. Okay, so in this slide, we just seen here the Terra is like a earth, and Aqua, AER is like a air, and Ignis is like a fire, and Aqua is like a water, because these are the five essential component in our earth. So same thing in the IBM Qiskit, it is like a earth, and what are the essential components are required for the implementations of real quantum system. Now the Terra is like a foundation layer. It is building a quantum circuits. How many gates are used in your system, like CCX gate or CX gate or swap gate. Okay, so all these is the basic component to implement a quantum circuits. So the Terra is the visualization of a quantum circuits. Okay, if you know the quantum circuits, then you can do the simulations or do some calibrations or do many benchmark performance parameter. Okay, another thing is the Qiskit era, which is it is like a simulations. So of course in the backend, if we run the simulations, so that means we get an exact qubit output in the measurement phase. And the Ignis is like a calibrations to do some noise analysis, bit flip or depolarized. Okay, all these noise analysis we can done by the Qiskit Ignis layer. And Aqua is like application developments or a new algorithm developments, which is will be for various applications like physics, chemistry, or machine learning applications or AI applications, and do some many optimization in the medicine discovery or the smart city. Uh, some new sensors, so because everything we need a new way of developing an algorithm. So in that case, the developer needs a aqua layer. Okay, so in this slide, I just give you the short form of all these layer description. Like Terra is like a building of quantum circuits, Era is like a simulations, and Ignis is like to measure the noise and error. And the Aqua is for application or algorithm development. So in this slide, we have seen how the reversible circuit have a one-to-one mapping between an output and uh, this reversible circuit go to the RC viewer for the optimization purpose, because the RC viewer have a template based optimization technique to reduce the number of gates and minimize the circuit depth and eliminate the redundant operations in a quantum circuits. Okay, so if we optimize the quantum circuits by this template based matching technique to reduce all these redundant gate or minimize the circuit depth, and this quantum assembly code to be mapped to the IBM Qiskit. Okay, so the optimized circuit translated into Qiskit, that is a second level approach. Okay, so the optimized circuit go to the uh, Qiskit for compatible format. Okay, because these two uh, uh, tool have a different compatibility. Okay, so in this Qiskit, there is a different capability. So we have to convert the code into the Qiskit format, and then the Qiskit code will go to the quantum hardware with our API key, okay, in the online server, and then execute on the real device on a IBM quantum computers, and then we have to see the benchmark performance parameters. Okay, so in this slide we have already discussed all these layer features. What is the feature in the all these layers? Okay, so in the what is quantum hardware? So quantum hardware is like a real hardware. So Terra is the interfacing device to interconnect the software and hardware. Okay, because we have seen in the whole Earth there are many components have a different significance. Same thing in the IBM Qiskit also, how these layers are build a real quantum circuits. And ERA is for the simulations, and Equa to develop algorithms, or the Ignis is for the noise and characterizations. So here I am showing in this slide how the backend library files, or the some export how to export a library files for all these layers, because every designer have a different approach. Okay, some person are interested in the quantum circuits or do the qubit measurement, but some engineers are working on the simulations. Okay, and some person are checking the noise in the quantum circuit. So in that case we need a different layers. So here, this is a code to check the circuit design part, how many gates are there, what are the types of gates in this era layer, AR layer. We have to see the simulations mode or the qubit measurement results, and this Ignis is to measure the noise with the help of this library file, and the Ignis is used to develop a new algorithm with the help of these two library files. Okay, so in the last slide, I just shown you the overall performance, overall comparative analysis of all these layers. Okay, so we can see that Terra is used for building and optimizing, and Era is used to test the circuit, and Ignis is to characterize the error or error mitigations, and Aqua is to apply a new algorithm for high level applications for a system design or some new system design with the help of quantum technology. Okay, so thank you to all to listen this presentation. Thank you very much.